So our next speaker is coming to us from NASA, and he's a regular at these meetings. You might also recognize him as the guy who played guitar on the Zoom meetings during the pandemic, but this is John Bolten.
Thanks. I did bring my banjo, so maybe
Next time for sure.
Yeah, thanks so much. I think Matt's presentation was great when talking about hydrology and the importance of soil moisture. You can go in many different directions, but I think this idea of translating in situ observations and modeling to a watershed scale is key, especially for what we do. Most of what I'm showing today is not my own work. I have the privilege of working with a great group of scientists at the NASA Goddard Space Flight Center Hydrological Sciences Lab. A few of them are mentioned here. So, it was great to hear Tyson this morning give his presentation, and I wrote down on my notes here what Tyson said: the importance of having soil moisture being widely available and readily understood. I love that. I love that concept, and that's the big challenge. Another challenge we have, and I have at NASA, is reminding people of the importance of soil moisture and how it relates to earth science as a system of systems, as we say. So if you didn't know, the soil moisture is woven all throughout the hydrologic cycle. But most importantly, it provides an understanding of the hydrologic cycle. It helps us understand the processes of this terrestrial water cycle, of the energy and carbon cycles, how they're all woven together. So we're all really have this challenge of taking this soil moisture observations at frequent temporal and spatial scales as much as we can, and having this be readily available and readily understood, as Tyson said. So that's the challenge here. And also translating these observations to a watershed scale, to a regional scale, and to a global scale. So if we go back on this figure here, and I don't think it's listed, but towards the left is the first time I met Mike Kosh. It was around 99 or 2000, I think, one of the early soil moisture experiments. But essentially what you see here is this evolution of satellite-based observations and soil moisture remote sensing. Off to the right of the slide, you see future missions, which I will mention here in a couple moments. But essentially, we are trying to push the science forward and, again, translate these observations that we understand are so critical, just the near surface soil moisture observations, to this regional scale capacity. So I borrowed this slide from Marena. I said, hey, I really like this idea of the three-legged stool. Again, reminding us of the importance of developing real-time, high-resolution, gridded national maps and user-friendly products. And I think that's job security for me and the folks I work with, is taking this information and as much as we can, making it available to the public. And I've been very, very fortunate to work within the applied sciences of NASA. And essentially, this is taking all the great work that you all are doing, that we're doing across in the hydrological sciences, and making them relevant to decision making. And that's where the fun happens. However, fun isn't always easy. So how do we translate these data to actionable information? The idea here is to synergistically blend Earth observations with field and management information. So whether or not you're focused on agriculture or flood forecasting, the key here is teasing out the most relevant information into a data integration analysis framework that is available to everyone. Now I'll go back to the premise of this entire presentation was the widely available and readily understood information that we're so eager to have at our fingertips. And ultimately, this will drive more informed decision making. So I'm going to breeze through a few of these slides, but essentially the takeaway from this slide is we have a long legacy at NASA of trying to address these questions of how do we monitor soil moisture. And from the vantage point from space, we have a great ability to do this on frequent timescales and over a large geographical extent. So some examples of soil moisture applications, just some examples of of how we're doing this in operational fashion. And just today alone, we've had examples from the livestock forage program from Tyson. We've also heard a great bit about the U.S. drought monitor. In addition, we are seeing that more and more satellite-based observations, which I will remind you are really driven, their accuracy observations are driven by what we observe on the ground, into weather forecasting, very, very strongly tied to agriculture applications and operations. The U.S. Drought Center, which I mentioned already, the U.S. Forest Service, which we have several folks in the room today talking about this, and our ability to take the relevant information from soil moisture and constrain the states and fluxes that are needed for these decision-making activities are key. So this figure right here is pretty telling. What this is just the number of unique users within a 30-day window of the soil moisture active passive SMAP L3 and L4 data. And if you can't see the left or the y-axis, this is, let's see, in July, we had upwards of over 500 unique users a week. So what we're seeing here is there's more and more need and more users of satellite-based observations of soil moisture. I have a few examples. This slide was produced by Hung Lei at NASA Goddard Space Flight Center. This is just from the Maui wildfires. And this isn't soil moisture. What you're seeing here is MOISST-based NDVI from the past 4 years. And what we're seeing is this looking at the above normal vegetation and the anomalies of vegetation conditions and relating this to soil moisture as a leading indicator of future conditions. What we're trying to say is, well, hey, let's first look at wildfire fuel load in the Maui fires, see how these compared with previous years, and what was the relationship to soil moisture? Do we have an ability to leverage soil moisture observations either from in situ or from satellite and provide a more informed and advanced look at wildfire risk and analysis? This isn't a solution to the problem. This is just basically us saying, hey, what's it look like? And how can we contribute to mitigating those impacts? So going back to this whole idea of weaving in situ observations and modeling capabilities is key at NASA Goddard Space Flight Center. So what you see here is this Earth System Modeling Data Assimilation Framework. This was provided by Sujay Kumar within the NASA Land Information System. But what we're seeing is that this evolution from mission development, science data processing, all the way through hydrological applications, we're seeing this foundation of science and research related to soil moisture, which is key in all of this. And we've just the last presentation, the presentation before that, on the LDAS capabilities, soil moisture is ever present in this. So the next few slides will be examples from, and this one is the U.S. Air Force, how we are taking this ability to model near surface soil moisture, incorporate and integrate observations, in this case of the soil moisture active passive measurements, and to help and drive and constrain U.S. Air Force capabilities of land surface modeling. And so this was a major endeavor done by NASA, by Sujay Kumar and Rajat Benlish. And what we're seeing is this is reducing the uncertainty of those land surface models. So if you look at, scaling up to a regional scale, what does soil moisture tell us in regard to, in this case, we're looking at two flash drought events in 2016 and 2017. One was more of a temperature driven event. One was a depletion of precipitation. But by taking in if you look at a time series of soil moisture from 2016 and 2017, we're able to isolate the times and areas of rapid depletion of soil moisture that caused this precipitation deficit driven flash drought in both events. And so what this is allowing us to do is approach this from a systems-based perspective and get a better understanding of how and why these events happened. As our models increase in fidelity, we're able to have more informed decisions. That's the goal from this. What's really interesting, this work was done by Joe Santinello and Patricia Lawson. And what they're seeing is, as we see an increase in irrigated land in the United States over the years, we're also seeing an impact from that irrigated land on regional climate. So they've done a lot of work in saying, well, how can satellite-based observations of soil moisture allow us to detect irrigation areas and times? This picture was just taken a few weeks ago. This was Karen St. Germain, several folks from NASA. We went on this, we called it the Space for Ag Tour. We went out in Iowa and we sat and listened for an entire week with farmers. And we met with the Iowa Corn Growers Association, 2 members of Congress. And we did this last year as well. And it was extremely rewarding for all of us, because what we learned was there's a lot of work that is being done in agriculture that essentially is critical for us to understand the value of soil moisture. And this is my little tease to go over and look at our team from Goddard, Ed Kim and his crew, from their SLAP instrument as well. We hope to actually fly this across Iowa in a couple months. So I didn't get through all my talk. I'm going to speed through because I was very ambitious with a lot of this work. I said, hey, everyone, if you have some relevant work, send it to me. But as far as the ability of soil moisture to lead to agriculture forecasting, we're dialing in this ability to tease out as a leading indicator of wildfire risk and analysis, which I also showed as well. Here, if you just take these figures here, we're seeing 65, 80%, and 75% of counties improved of matching end of season yield. Okay, this is based just on a satellite-based observation of soil moisture and MOISST NDVI. So this is a significant increase in our dashboard-based surveys of soil moisture. So I'm going to end it with a few things. So I'll go back to this message of community building. But what I'm seeing is this bridging of the gap between soil moisture characterization through strategic blending of in situ and land surface modeling is key. We are now have an increased ability to access, analyze, interpret, and contribute to these soil moisture information capabilities. But the need for standardizing data access and sharing through increased leveraging of cloud-based services, machine learning, we've heard about that today already, and machine learning, again, I repeated it, is a critical part. So hopefully this next time series that we'll see this evolution of remote sensing capabilities of soil moisture will incorporate future observations. I skipped over a few slides of our Indian Space Agency and NASA collaboration for NISAR, which is expected to launch next year. And we have other activities on the horizon. So thanks so much. And I'll take questions if we have time.
All right, questions for John?
Thank you. Is there anything in the works for soil moisture comparable to like open ET for evapotranspiration, especially at that, field scale, resolution, maybe post NISAR, India?
Yeah, that's sort of the pie in the sky, I think. So if you're not familiar, the open ET is a sort of a collaboration of a multi-model cloud-based access to evapotranspiration. To my knowledge, there is not an open SM at the moment, but I think that would be a wonderful target. I know that I mentioned some of the figures I showed were Google Earth Engine based access to SMAT based soil moisture. We really would love to see a model based equivalent of that and a multi-model based equivalent to that. So short answer is no, not yet, but we should talk afterwards. Thanks.
Other questions? We got one online. All right, so we have a question from Manab online saying, I'm generating surface volumetric volumetric soil moisture using Sentinel-1A VH plus VV polarization SAR data at 10 meter sampling at 25 meter resolution and measurements at 0.25 HA. I don't know what that unit is supposed to be. I'm so sorry. Or better every 12 days. The accuracy is 13%. Why is there reluctance in using higher resolution and instead downscaling technique to artificially produce high resolution?
Oh, that's a good question. So that's on the chat. I think I'll reply.
Okay.
Yeah, reply. That's a fantastically detailed question. Yeah. Thank you.
Yeah.
I feel like you kind of skipped over the irrigation and weather relations, and I would love to learn more about that. Can you cover it briefly or refer us to a place to go?
Yeah. So Patricia Lawson from NASA and Joe Santinello, they have a GRL paper published in 2017 and a couple other relevant publications. But what they do a lot of boundary layer science, looking at this land atmosphere dynamic and sort of constraining them within a modeling capacity. In addition, what they're also showing is the utility of SMAP observations for identifying areas of irrigation and sort of characterizing that. So if you will. So in short, they're saying, okay, first of all, we are seeing an impact from the irrigated lands in a modeling sense, and also from satellite-based observations. How can we also identify areas of irrigation from satellite observations of soil moisture? So yeah, Patricia's doing some very, very interesting work. I'll follow up with you and share some publications with you. Thanks.
Thanks again, John. That was great.
Thank you very much.
Manab, I'm so sorry if I butchered your question.